Thank you very much for giving me opportunity to talk about my recent research today. Also, I'd like to thank my co-authors for all the collaborations we performed together. Our work has been recently accepted in the ACS Applied Materials Interfaces, and we are preparing for publication now. And the other manuscript has been published in Micro Machines. Okay, today I will talk about chemical composition and its control at iron cyanide MgO interface. First, I'd like to briefly introduce iron-based superconductor iron cyanide, which already Shimojima sensei already talked about. It is the structurally simplest of the iron-based superconductors that consists of a square lattice of iron bonded with selenium ions which sit above and below the iron plane. Iron cyanide thin films have been grown on various substrates by pulsed laser deposition (PLD). This table shows some examples of the substrates with relatively small initial misfit strain. They are aerial, calcium fluorine, and SDO. When the films are grown with a thickness larger than 100 nanometer, they exhibited superconductivity at temperatures ranging from 7 to 15 Kelvin. In case of calcium fluorine, chem studies show the formation of calcium cyanide interfacial layer, which slightly reduced the initial misfit strain to 1%. In case of MgO, there is a large initial misfit strain of 10%. Nevertheless, it has been reported that monolayer iron cyanide has been grown on MgO with cube-on-cube texture by molecular beam epitaxy. In fact, chem studies of the interface show that 11 unit cells of iron cyanide match 10 unit cells of MgO, which indicates the initial misfit strain was largely reduced to 1.3%. To understand what governs the epitaxial growth of ultra-thin iron cyanide films on MgO, we have investigated the interfaces of PLD-grown iron cyanide MgO thin films with thicknesses around 20 to 30 nanometer. However, there are some enduring challenges in PLD of iron cyanide thin films. To achieve stoichiometric transfer of material from target to substrate, one needs to control volatile elements such as selenium during target ablation, film expansion, and film nucleation. In addition, one needs to control the chemical bonding between films and substrate, film growth modes, and film strain. After producing films, the film surface needs to be protected from oxidation. With these constraints in the purity of iron cyanide thin films, there are two important factors to consider: strain and chemical composition. The strain at the film-substrate interface affects structural parameters such as lattice parameters and textures, whereas distribution of chemical composition at the interface induces interface layer formation or chemical diffusion. These effects are connected with each other and eventually related with superconducting properties. Therefore, our study is to elaborate how these factors are related with each other and complicate the growth of ultra-thin iron cyanide films that should be grown epitaxially and superconducting. This slide shows the contents of my talk today. Now, let me first explain the sketch of the iron cyanide MgO header interface. As I mentioned before, the initial misfit strain between iron cyanide and MgO is about 10%, which is too large to allow conventional lattice matching epitaxy LME. Nevertheless, it is still feasible to grow epitaxial iron cyanide films on MgO with cube-on-cube texture because of domain matching epitaxy DME, where N unit cells of iron cyanide match N unit cells of MgO across the interface. In case of a clean iron cyanide MgO interface, we confirmed that the ideal DME happens with M over N equals 11 over 10, 10 over 9, or 9 over 8. They are consistent with the DME theory by Nayan and Larson. Apart from such ideal case, we demonstrate that real interface is much more complex and chemically heterogeneous due to iron segregation and MgO. We propose one engineering solution, which is iron buffer. The advantage is to achieve chemical homogeneity at the interface. The potential disadvantage is ferromagnetic effect. We suggest that LME can be achieved at the iron cyanide iron interface that is advantageous for superconductivity. Furthermore, we will show that with different deposition conditions, a different iron cyanide iron texture can be also obtained. Now, let me move on to structural characterization of iron cyanide MgO films. This figure shows 2 theta omega XRD scans for iron cyanide MgO films grown at various substrate temperatures Ts. The pink shaded region illustrates the growth of C-axis oriented tetragonal iron cyanide films for a temperature regime between 240 and 500 degrees C. Next, please look at the 4 figures of iron cyanide 101 and MgO 2224 figures. And they show the relative in-plane orientations. The majority is oriented 100 iron cyanide parallel to 100 MgO, which is cube on cube, whereas the minority is oriented 100 iron cyanide parallel to 110 MgO, which is 45-degree in-plane rotation with respect to majority. By comparing these 4 figures, we can see that pure cube-on-cube texture was only obtained for the film grown at 500 degrees C. Next, let me compare the changes in textures with respect to Ts in detail. The average intensities of the reflections for the 45-degree rotate textures, I45, is strongest at 260 degrees C and decreases with increasing Ts. On the other hand, the average intensities of reflections for cube-on-cube texture, ICC, increases with increasing Ts. I will discuss this temperature dependence later with respect to strain variation. In contrast to the changes in textures, both C-axis and A-axis lattice parameters of iron cyanide films show almost linear temperature dependence. Now, let me explain our 10 observations of the iron cyanide MgO interface. This figure shows the cross-sectional stem images of the films grown at 500, 400, and 360 degrees C. The cubic lattice of the MgO substrate can be seen at the bottom, whereas well-ordered iron cyanide layers are visible on top. The yellow lines represent the domains. We can identify domain matching ratios of m over n equals 11 over 10, 10 over 9, and 9 over 8. By assuming that these domains are equally distributed at the interface, the initial mixture strain of 10% was now largely reduced to the actual residual strain below 1%. These ratios are consistent with predicted values. Now, let's look at the composition distribution at the iron cyanide MgO interface. This figure shows the cross-sectional 10 EDXs image of the film grown at 360 degrees C with a thickness of 14 nanometer. Red and green colors represent the distribution of iron and selenium. We can see an iron-rich layer at the film substrate interface. This can influence the local distribution of strain, which I will discuss later. Also, we found a 3 nanometer thin iron-rich layer at the film surface. In total, an inhomogeneous distribution of iron and selenium was found around the film cross-section. This heterogeneous interface environment can explain the variation in domain matching ratios. Let me explain the effects of iron excess at the interface on local strain distribution. These figures show examples of geometric phase analysis of films grown at 240 and 400 degrees C. The black circles represent misfit dislocation faults, and the color contrast carries information of nanostrain in the film. The more dislocation chords appear, the more relaxed the film becomes. The film grown at 240 degrees C has higher contrast and contains more nanostrain than the film grown at 400 degrees C. This suggests higher strain state in the film grown at 240 degrees C. This is consistent with the result of four-figure measurements, where I45 was higher in the film grown at low temperature, suggesting a higher degree of texture homogeneity at the interface. To decrease the chemical inhomogeneity at the interface and minimize the inhomogeneous interface strain, we propose one engineering solution, which is iron buffer. This figure shows two theta omega scans of the iron cyanide MgO film grown at 240 degrees C and the iron buffer film grown at 250 degrees C. We can see that the film still remains Z-axis oriented. This figure illustrates a typical resistivity versus temperature curve of iron cyanide MgO film at 0 Tesla, which shows a semiconducting behavior. This is consistent with previously reported suppressed superconductivity in iron cyanide MgO films. On the other hand, iron buffer films show a complete superconducting condition with Tc onset equals 3.8 Kelvin. Next, please look at the 1014 figures of iron cyanide and iron and 222 reflection of 2224 figure of MgO. Which confirms the in-plane texture is 100 iron cyanide parallel to 110 iron parallel to 100 MgO. Now, I will explain our 10 observation of the iron cyanide iron interface. Consistent with four-figure measurements, we confirm the 45-degree rotate texture of 100 iron cyanide parallel to 110 iron. The initial mystery strain now reduces to 7%. The predicted domain matching ratio is 14/13. Consistent with this prediction, we confirm several domain matching ratios of m/n equals 15/14, 14/13, and actual residual strain is now 2%. According to Nair and Larson, when m/n is bigger than 13/12, the DME is identical to conventional LME. Therefore, we conclude that LME has been realized in the iron buffer layer film. Because of LME, the iron cyanide iron interface is coherently strained. Consequently, compared with the lattice parameters of iron cyanide in the iron cyanide MgO film, a slight decrease in A-axis and an increase in C-axis have been confirmed in the iron buffer layer films. In addition, the iron cyanide iron texture can be modified by slight variations in deposition conditions such as temperatures and film thicknesses. Please look at this 10 image of the iron cyanide iron interface. The 45-degree rotate texture was converted to cube-on-cube texture of 110 iron cyanide parallel to 110 iron. Accordingly, the initial misfit strain expands to 31%, which no longer supports LME. Only DME is possible with predicted domain matching ratios of m/n equals 2/3. Consistent with this prediction, we confirm domain matching ratios of m/n equals 3/4, 4/5. And the initial misfit strain was largely reduced to 4%. The difference in iron cyanide iron textures can be attributed to slight variations in deposition conditions. This table compares gross parameters and layer thicknesses. In the iron buffer film, 45-degree rotate texture changes to cube-on-cube texture with decreasing TS. In contrast, at iron cyanide MgO interface, 45-degree rotated texture changes to cube-on-cube with increasing TS. This comparison suggests that the texture is governed by iron buffer roughness and growth temperatures. However, detailed analysis is still needed in future investigations. Let me now discuss the implications on superconductivity. The anion height of selenium ion from the iron layer in the iron cyanide unit cells, denoted as HSE, can be estimated by this equation, where GSE represents the Wyckoff position of selenium in the unit cell. We assume that Z value of bulk iron cyanide is the same for thin film. HSE was calculated to be 1.510 for iron cyanide MgO with DME and 1.537 for iron buffer film with LME. Therefore, HSE was enhanced in the iron buffer film, which leads to a superconducting transition. In contrast, although the iron buffer films with DME has a higher HSE than that of iron cyanide MgO, it did not show superconductivity either. Let me summarize my talk. We have confirmed the DME occurs at iron cyanide MgO interfaces with various domain matching ratios. Consequently, the initial misfit strain was largely reduced to the actual residual strain below 1%. But in reality, we demonstrate the iron cyanide MgO interface is heterogeneous and iron enriched. Furthermore, iron segregation in MgO makes the properties of iron cyanide films less controllable. In conclusion, we have demonstrated the growth of rotating iron cyanide films using PRD demands the control of the chemical composition at the film substrate interface. Lastly, I'd like to share the two links again for our manuscript. Thank you very much for listening.